Hello everyone, in this video we will learn about types of geometric progressions and the sum of infinite GP. There are two types of GPs we have. Number one is finite GP. What is a finite GP? The name itself tells. There are finite number of terms or definite number of terms. So we say it contains finite number of terms. For example, we can say if it is 2, 4, 8, 16 and so on, and it goes up to 108. So we find there are finite number of terms. That's why it is a finite GP. One more example we may have, suppose it is 3, 9, 27 and so on, and it is given 15 terms. It means it contains only 15 terms. That is also a definite number of terms or finite number of terms. So it is also a finite GP. And we have already learnt about finding the nth term and the sum of n terms of a finite GP. The second type of geometric progression we have is infinite GP. Here also we find it contains infinite number of terms. So we say contains infinite number of terms. For example, first example we have 4, 12, 36 and so on. It continues up to infinite, and that's why this is an infinite GP. Here we find R is 3, that is the common ratio. Second example we may have 16, 8, 4 and so on. It is also an infinite GP, and here the common ratio R is 1/2. So we can differentiate between the two types by the number of terms. Now we will discuss about finding the sum of an infinite GP. We take the GP here AR square and so on, and it contains infinite number of terms. Before finding the sum of this, we have to see what is the common ratio. Here the common ratio is R, but what is its numerical value? We can have the cases, number one, if R is equal to 1, then what we see? Then we find the sum will be A plus A plus A, up to infinity it goes. And then the sum itself will be infinite or not. The second case we may have, if R is greater than 1, then what we find? Then the sum increases as the number of terms increases. So we can say the sum increases as the number of terms increases. Here also we find that in case we want to find out the sum of infinite terms of GP, what we will find, this is A plus AR square and so on, we go up to infinity, that will also be infinity. For example, suppose we have the GP as 2, 8, 32 and so on. We find here R is 4. When R is 4, if we find the sum of one term, that is 2. Sum of two terms is 2 plus 8, that is 10. Sum of three terms comes as 2 plus 8 plus 32, and that comes as 42. And so on. What we find, when the number of terms is increasing, the sum is also increasing, and hence we can say that in such cases the sum of infinite terms also will go to infinity. It will be very large. The third case we have when R is less than 1, and then the sum of infinite terms A plus AR square can be found by formula. Why it is possible? Because if R is less than 1, the value of r to the power n reduces with the value of n increasing. So when n increases, the value of r power n reduces. We can say for an example, suppose r is half. What will be r square? That will be 1 by 4, which is less than 1 by 2. If we find r cube, that is 1 by 8, which is less than 1 by 4. And so on we find when n increases to infinity. It means when it goes to infinity, we can say the value will be tending to 0. It becomes negligible. In such cases, we can find out the sum of the infinite terms of the GP. This type of geometric progressions are known as convergent GPs. We call them convergent progressions. Now we'll learn how to find out the sum of infinite terms. If the GP is A, AR, AR square and so on, the common ratio is R and the first term is A. We know that sum of n terms Sn is given by A into 1 minus R per n upon 1 minus R when R is less than 1. This we have already learnt in the previous videos. In case we want to find out the sum of infinite terms here, sum of infinite terms will be A into 1 minus 0, as I told you that R power n will be tending to 0, that is nearest 0, or we can say negligible, upon 1 minus R. It means this comes as A upon 1 minus R. So we will be using the formula for the sum of infinite terms of a GP where R is less than 1 is A upon 1 minus R. Let's take some examples to understand how to apply the formula for sum of infinite terms. The first example we have here is find the sum of the GP 36, 12, 4 and so on. To find the solution, first of all we write the GP which is given to us is 36, 12, 4 and so on. Here we find the common ratio R is 1 by 3. A, the first term is 36. When we want to find out the sum of infinite terms, the formula is A upon 1 minus R. A is 36, 1 minus 1 upon 3. We can write this as 36 upon 2 by 3. Or we can write this as 36 into 3 by 2. This cancels this as 18. And 18 3 ja 54. So the sum of infinite terms of the GP is 54. Like this we can find out the sum of an infinite GP. We discuss one more example on the sum of infinite GP. That is, find the common ratio of the infinite GP in which each term is twice the sum of the terms following it. When we want to find out the solution of this, we can consider the GP. We can write let the GP be A, AR square and so on. Then according to problem we are given that any term, that is suppose nth term, will be twice of the sum of the terms from n plus 1 to infinity. Can we also write this as an equal to twice of, we know the n plus 1th term is a into r to the power n, plus next term is arn plus 1 and so on, it goes up to infinity. We know the value of this, that is a r power n minus 1 equal to twice of the sum of infinite GP. We already know the formula, sum of infinite terms is a upon 1 minus r. Here we have the first term as a into r power n. So we write a into r power n upon 1 minus r. Do we find here this a and this a cancel? And if we simplify it here, we can write that 1 minus r is equal to 2 into r power n upon r power n minus 1. Do we find it is 1 minus r equal to 2r? Or we can say 3r equal to 1, it means r comes as 1 upon 3. We can also do it by one more method, that is second method we can have. We take only the first term. According to problem, if we go for the first term, then first term is equal to twice of the second term, that is AR, third term AR square, and so on up to infinity. This gives us A equal to 2 into, here first term is AR upon 1 minus R. A and A cancel, and we are getting here 1 minus R equal to 2R, which gives us R is equal to 1 by 3. So anyway we can find out the answer, we can show it theoretically, and also we can take one particular term and then we can find out the sum of the next terms, which is twice of it. We discuss one more problem, that is if x equal to 1 plus a square plus so on up to infinity, and y equal to 1 plus b square up to infinity, then prove that 1 plus a into b plus a square into b square plus so on up to infinity is equal to xy upon x plus y minus 1. It is given that modulus of a and modulus of b are less than 1 each. To find the solution of such problem, what we do, we'll write here x equal to 1 plus a square plus so on up to infinity. And it is given that a is less than 1, which is the common ratio of this. Then we can apply the formula, sum of infinite terms is a upon 1 minus r. In this case, the sum here will be 1 upon 1 minus a or not. If we cross multiply it, we are getting x minus ax is equal to 1. We can get from here ax is equal to x minus 1. It means a is equal to x minus 1 upon x. Similarly, we write y equal to 1 plus b square up to infinity, where it is given that magnitude of b is less than 1, and this is the common ratio here. So we can write this y will be 1 upon 1 minus b. And with the similar simplification, we can get the value of b as y minus 1 upon y or not. We also know that if magnitude of a is less than 1, magnitude of b is less than 1, certainly magnitude of a into b is also 1. This we have to apply for the given sequence. That is 1 plus ab plus a square b square plus so on up to infinity. We find here the common ratio r is a into b, which we have shown is less than 1. So can we find the sum of this will be a upon 1 minus r, that is 1 upon 1 minus a into b. Substitute the value of a and b, we are getting 1 upon 1 minus, what is a? X minus 1 upon x. What is b? Y minus 1 upon y. Taking the LCM here and simplifying this, we will be getting xy upon x plus y minus 1, which we had to prove. Like this, we can solve the problems based on the sum of infinite terms of an infinite GP. In the next video, we will learn about some special sequences. Thanks for watching my video. If you have any comments or doubts, leave them in the comment box and I will get back to you.